What's the problem about? Or what's the decision? No, what's the decision? I'm not asking the objective yet. What is this person trying to decide?
What type of goal to mine?
Which type and where?
Which type and where?
The 3 different grades of coals at the 2 different plants.
Right, but when you schedule extra shift of worker at a mine, all 3 types will be produced, right? So it's not where. It's not which type at where. It's like,
schedule an extra shift or not?
okay, very simple, right? To schedule extra shift at each of those mine or what? Okay, and it said they can only schedule one, so here, only one additional shift can be scheduled each month at each mine. So we're trying to determine, say, how many months of extra shift should be scheduled at each of those places. Okay, say for example, we decide that, okay, we need to schedule 4 extra shifts at Miss Y and 2 extra shifts at this place. That means we are actually scheduling 6 months. Does that make sense? Okay, and how to meet this extra increase, right? Let me just highlight them. So why do we need to make this decision? Is because, okay, there's some increase in demand. Okay, so we want to meet those increase in demand. Okay, and with some objective. Where are the objectives? So what are the objectives?
Maximize the mine coal and then minimize the health problems, accidents.
Maximize total tons of coals. How can you maximize that? Because they are already determined, right?
Because you have a demand, then you have to schedule the shift.
So the demand is already set. If you maximize the production,
You want to minimize your additional cost to run.
okay, minimize the additional cost to schedule those shifts. Okay, so here, okay, so it costs money, right? Costs money to schedule additional shift. Okay, so here, I will say that's one objective. We want to minimize the total cost. Okay, any other objectives?
You want to minimize the pollution.
Okay, so they said that toxic waste, right? He is concerned about the environment, doesn't want to create any more pollution than is absolutely necessary. Okay, so here. So that gives us the second objective. Okay, so he wants to minimize the pollution too. Okay, anything else? Accident, good. Okay, so there are some accidents happening there. And so she cares about the health and welfare here. Okay, so that gives us our third objective. Minimize the number of accidents. Okay, so we kind of analyze this problem. So this gives some general information. Okay, so to these two mines, 3 different types of coals, high grade, medium, and low grade coals are produced at different production rate. Okay, and also cost per month to shift to schedule this extra shift also differs. Okay, and toxic water and life-threatening accidents also listed. And to meet this demand increase, which is 48 more tons of high grade, 28 more tons of medium, and 10 tons of low grade coals, while meeting these 3 objectives. The decision is to see, okay, how many extra shift I should schedule, not Blackstone Mining should schedule here and here. Okay, is this clear? Okay, so the decision variable would be number of months to schedule an extra shift at each of those mines. Okay, which is pretty easy. And to meet those demand, very easy LP problem for you guys now. The high grade coal needed is 48 tons, and based on what we have here, okay, so 12 tons and 4 tons are produced at each of these 2 mines. And to meet this 48 tons of high grade tons, we're going to add these together. Okay. Same for the medium grade and low grade coal. Okay, so we have 3 constraints here now, and non-negativity conditions. Okay, so this represents a really simple LP model with 3 different objectives. Okay, we talk about, okay, the 3 objectives would be minimize the total production cost, minimize the total toxic water produced, and minimize the number of accidents. Okay, then how do we handle these multiple objectives? If the if those objectives, which are those 3 ones, have target values, then we can treat them like those following goals. Okay, we say, okay, the total production cost should be close to this much, and the total amount of toxic water produced should be close to this value, and the total life-threatening accident should be approximately that value. And because in all the 3 objectives we want to minimize them, so we want to penalize the overachieving deviations, like what we talk about, right? Make sense? Okay, but the difference between this problem and the Go programming problem we talked about earlier is that we have those 3 objectives, but we don't know what the target value should be. Okay, and we know that we want to penalize the we want to penalize the overachieving deviation, meaning that the objective function would be to minimize the total weighted underachieving deviation as a percentage. Okay, but we don't have the target value here. Is there a way for us to find a target value for each of those goals? What do you guys think? We have the demand, but the demand is used as a constraint. Let me go back to the model here. So we have this model, right? The demand are used here as a constraint. And we have 3 objectives. And now our question is that, can we translate the 3 objectives to goals? Can we translate those objectives to goals? I mean, they mean different things in management, different levels, but here we just use the OR language. Okay, the objective here means our objective functions, and the goals means the ones that we treated in the Go programming part. And for the goals, usually we have a target value. If we say we have a goal, that means we have a target value. And here, those objectives we only know is, okay, we want to minimize those values. So we have those constraints, hard constraints, and we have 3 objectives, but we don't know how to deal with them. Okay, so what do you think? For example, in the previous problem, what does that 5 value means for the target value for the small room number. What does that 5 mean? Which is not here in the Go programming example. So we said, okay, the target value for the small room is 5. And in the problem statement, what we were saying is that, okay, we would like to have, it's desired to have at least 5 rooms, right? And here, this target value we're saying is, okay, the total cost is desirable to be a certain value. And this certain value can be just the minimized cost, right? Thinking this way. If we solve the problem, just use this objective, we can get a minimized total production cost. And that would be a desirable value to be achieved for this total production cost. We know that when all 3 objectives need to be taken into consideration in this OR decision, we probably won't be able to achieve that production cost at exactly the same level. But that's kind of like the best production cost that we can get. And as long as we are getting close to that target, then that's great. Does that make sense? Okay, so that's the same for these 2 other objectives. Okay, so we can solve each of those problems individually. So we solve the model 3 times with one of these objectives each time to get what's the most satisfying level of the product cost, the most satisfying level of the toxic water produced, and the most satisfying value for the accident number, and use those numbers to be our target value. We know that eventually we will deviate from all of them for sure if we can find a balance among all the 3 objectives. But that's the best value we can go. Okay, as long as we minimize the deviations, then we achieve our goal. Okay, so, oops, sorry. So that's here. So we can solve 3 separate LP problems independently, optimizing each objective to find the value for T1, T2, T3. Okay, so if we go to this Excel spreadsheet, the second one that I have here, the MOLP. So I already listed all the values required. Basically what I'm trying to do is solve the 3 different objectives. And this problem is really simple one. It's kind of like that Blue Ridge hot tub that we talked about first. Okay, so we'll have those resources, not resources, the different level of goals produced and the required. So let me see. So I'll just see the number. Okay, so you can follow me in setting this part up. We're actually going to use them later. Months to operate. And I'll insert a row here. Okay, and highlight these 2 as my decision variables. So that's our decision variables. That's how many months to operate to add that extra shift. And here I will put produced to be the left-hand side of my constraints. Okay, so this table here represents the different levels of coals produced per month at each of those mines. And if we add extra shift, so the produced will be some product of these ones and these ones. And I want to fix this row here. So that's the B2. That's the row number. I'll put a $sign before the row number, so it won't shift when I copy it. Click. Okay. So it's the months, the extra months to add the shift times the unit of coal produced and put sum them together. And these are my left-hand side. And those are the only constraints we will need to solve the problem individually. Okay, and then here, I'll put the objective here. We have 3 separate objectives, but the formula are the same. If we go back to look at here, the formulas are all sum product of those rates and the decision variables. Okay, so I'll put all 3 in. Objectives equals to be the sum product. Actually, we can copy what we had here. We can copy this. To here. Click. Yeah. Because they take the same format. It's the sum product of decision variables and the values here. So you can basically just copy a cell from the constraint left-hand side and all the way to here. But change the color coding. So all the formulas here are the same. Objectives. You guys all done? Okay, then we'll just go to solver, solve each of them individually. So first, you select this as the objective. Okay, select the first objective, this one, and you want to minimize it. Click OK. Variables will be, oh sorry, these 2. Click OK. Constraints will be produced greater than or equal to required. Click OK. Okay, so these are my solver setup. Made them non-negative. And we assume that you can schedule shift the partial months. Okay, so we won't need to add the integer constraints to the decision variables. And change the algorithm to be LP. Solve. Okay, so you see, now we solve this problem based on the first objective, and we get a value. That's 244. Just write it down. Okay, we'll put the optimal. So the optimal value for this cost is 244. Then, and you can see like the toxic water is really high, 7,625. Accident is 2.5. Okay, then we're going to solve the problem for the toxic water. Minimize toxic water. So basically, click on your objective, click change, and change to the second objective. Still minimize it, solve. Okay, now, well, decreased about 1,000. Okay, so put the optimal value here. So 6990. Oh, sorry, 6950. But you can see that the cost per the total cost increased from 244 to 256. Okay, so that's what we talk about the Pareto optimal. When one objective one value for objective get worse and the other get better. Then change the objective again. Click change to this one, to the accident part. Solve. Okay, so the minimum number of accidents you can get is 2. Then you can see when you minimize the accidents per month, oh sorry, the total accident number, this toxic water get really high, same as the cost. So total cost get 400 from this 244. Okay. So what do we got here? Those represent the best value that we can achieve for all the three objectives if we just keep one objective in mind. Okay. Then, oh. Okay. Then we'll look at that. So we can translate the three objectives to three goals. Okay. The first goal will be the total cost of production cost should be approximately 244. And second goal will be the gallons of toxic water produced need to be approximately 6,950. And the number of life-threatening accidents should be approximately 2.0. Okay. Then with this, you are able to write an objective now. If we just, and using that deviation, okay. And remember that in this case, we want to minimize all the three ones, which means overachieving is not acceptable. Overachieving is not desirable. Okay, and we want to penalize the overachieving deviations in the objective function. And the underachieving them is what? Can we underachieve them? Think about it. These are already the best values that we can get with a minimization objective, okay? Which means it's impossible to underachieve those values. No way, you cannot get less than those ones. Okay, so we don't need even to consider the underachieving deviations. Okay, so for only the overachieving. And our objective function, remember we want to get the weighted percentage deviation. Okay, so let me ask you how to write this first goal. So the weighted, we want to minimize the weighted percentage deviation. So W1 times the first goal. Okay, what's the deviation? What's the deviation of the first goal? We know that the target value is 244, right? Okay, what's the numerical part? If we don't use the D, we just calculate. Weighted percentage deviation. So before we used like a D here, right? So this part, this numerator part means that's a D plus. But I don't want to introduce this D to this problem. I just want to use my decision variable to represent the deviation. Maybe this is clearer now. So I want to minimize the weighted percentage deviation. I already put the target value at the denominator part, so we're calculating the percentage. But what do you have here? So what are these ones? What does this part give us? This part. That's the actual amount of production cost, right? And we do have our target value. So we know that if we achieve some balance, then this part will be more than this 244. But how much more? Can we calculate that? How much more? How much more is the deviation? Okay, subtract 244. Okay. Okay, look at this again. I minimize the weighted percentage deviation. Because it's percentage, so I put the target value at the denominator part first. Okay, and then for the numerator, what I wanted is the the D plus part. It's the overachieving part. So the overachieving, so this D plus equals to B. We're kind of like doing the opposite way. It's like the actual value. When it's at the border, it's hard to write. Value, actual value, subtract the target value. That's the same, it kind of like just change the format, right? In the Go programming, what we wrote is actual value minus this D plus, and then plus a D minus equals to B, target value. Okay, and what I wanted here is, okay, I would just let's just minimize the total weighted deviation, percentage deviation, which will be the D plus divided by the target value. So to calculate this D plus part, move this to the other side of the equation and move the target value here. And we know that there is no D minus because there is no way to underachieve this goal. So that's why we have the actual value subtract the target value here. Okay, so that's the first part. Okay, then let's write the second one. The gallons of toxic water deviation. Again, we know that this is the lowest value we can get. So there is no D minus in this case either. We only have a D plus. And we want to represent D plus using the same thing. Actual value, subtract the target value and divide it by target value. Okay, and actual value can be calculated in which way?
Minus 6,950.
Okay, minus the target value divided by the target value. Okay, good. Then write the third goal for me, please. The third weighted percentage deviation. What's the third goal? Third percentage deviation.
2 times x1 times x1 plus 145 times x2 minus 2.
Okay, divided by 2. Okay, good. So that's the function that will minimize the total weighted percentage deviation. Okay. And when we solve those three problems individually, that's the feasible region defined by those constraints. So those three constraints, like the high grade, medium, low grade demand need to be met. Okay, so that's the feasible region. And we had those three solutions represent those 3 points, each at the corner point. So this kind of like gives you a review on chapter 2's knowledge. Okay, so all the feasible solutions are in this region, and we find the optimal solution on those corner points. Okay, when we use those 3 different objectives, we find these ones. Okay, and when we use this objective function, which we just created, this is the same as the handwriting one. Okay, when we use this objective function and the same constraints, it's just a linear combination of those decision variables. So the original objective, so say the objective 1, objective 1 is to minimize 40x1 plus 32x2, right? The second objective is to minimize 800x1 plus 1250x2. And 3 is to minimize that 0.2x1 plus 0.45x3. So those correspond to, I need the previous one. those three objectives correspond to three different level curves, right? Okay, I don't know how they are drawn, but when we try to minimize them, right? So maybe like on this one it's minimized. So those level curve will be something like this. So the intercept on those will be minimized, depends on like the slope of those level curves. So you get those three different points. And when we change the objective function to this one, and we know that those three weights will be numerical values. They are not decision variables. Okay. Otherwise, this objective function is not linear. Okay. So those will be numerical values. And when you do the math and put them together, it's again a linear. It's a linear combination of those decision variables, just like these ones. Make sense? Okay, just like these ones and with a different slope. Okay, so when you solve this, this new objective will create a level curve which will be similar to one of them with a different slope. And will only generate solutions at the corner points of the feasible region. Okay, so that means, with this objective and the same group of constraints, we didn't add those deviation constraints like those soft constraints because we don't need them. In this case, we represented the deviation already in the objective function. Okay, but with the same constraints, what do you expect? We get the same feasible region, right? Feasible region is defined by the constraint. Okay, if we have the same constraint as before, what do we get is the same feasible region. And we said this new objective function is just a different way of linear combination of our decision variables. So when we solve the problem, what will happen? Depending on the weights given, the solution will still occur at one of the corner points. So we will still have this one or this one or this one. Does that make sense? Okay, so you will still either get this one or this one or this point when you try to minimize those total deviations. So that means we're not able to find the trade-off among those objectives. Okay, can we get something here or something here? So if we get something here, that means a trade-off between the production cost and the toxic water. Or somewhere here, that represents a trade-off between the toxic water and the accident. Or can we get a value somewhere here that may represent a trade-off among all the three objectives? Is that possible? It's not possible without changing the constraints, right? If we don't change the constraint, the feasible region will be the same, and you end up with having a solution at the corner point. Okay, unless you change the constraints, you will get a different feasible region, and one of the corner points in that new feasible region may represent a combination, represent the trade-off among those different objectives. Okay, so with that, to change the constraints, okay, we won't be able to use this one. Okay, so we need help from the minimax objective. So this minimax objective actually can be used in Go programming too, but we don't really use it with that minimized weighted percent deviation. What this minimax objective is saying is that, okay, let's just introduce another variable named Q. Okay, and this Q, make it greater than or equal to all the deviation variables. Okay, and minimize this Q. And what we are saying with this model is that, okay, now we minimize the maximum deviation from any goal. Okay, think about that, what we talk about, like the purpose of when we translated the 3 objectives to 3 goals. And we said, okay, let's just set some target value, which is the best scenario that you can get. And as long as you minimize all the deviations, then you will be fine. Okay, and what we first tried is minimize the total weighted percentage deviation. But we found, okay, by doing that without introducing new constraints, we're not able to achieve a balance among those 3 different objectives. What we will get when we solve the problem will be, will either be this value or this value or this value, same as we solve those different objectives individually. Okay, but that's what we don't want. What we want is, where am I? Okay. What we want is some value in between. Okay, so let's see. Oh, sorry. Let's just minimize this Q and make all the deviations less than or equal to this Q here. Okay, so instead of having that minimize total percentage deviation as the objective function, now we minimize Q. And we use what we created earlier in that objective function, representing the weighted percentage deviation to be the D's. Okay, so all the percentage deviation, weighted percentage deviation need to be less than or equal to this Q, in addition to the original constraint we have. Okay, so you see that in addition to these constraints, we add some more, which means that so just now the feasible region is something like this, and now we add more. And actually we cannot draw it now because we have more than 2 decision variables. It's 3-dimensional now. This Q is the decision variable too. Okay, so but we add more constraints, so that feasible region is changed. Now we maybe find some points that's in the middle of this feasible region earlier. Okay, so this objective will allow the decision maker to explore non-corner point solution of this feasible region here. Okay, so that's the final model we have for the MOLP. So let's implement this model here. Okay, so go to that spreadsheet you had. Create a copy for this one. Okay, just to make sure, to turn in homework in this chapter, for the problems on MOLP, you need both sheets. Okay, don't just work on this initial one. I need you to show this initial sheet that calculate the target values. Okay, and then you create a copy of it and continue to work on that to create that MOLP. Okay, so now back to here. In the MOLP, what we needed is first calculate the percentage deviation. Okay, weighted percentage deviation. And here we'll just assume that the weight will be 1 again at the beginning. So we have all those ones, and let's see. We're going to need, so I'm just going to delete this column here, because these are no longer the objective. Okay, and these values, I'm going to change them as target value. Okay, so how do we, so we will follow the same format here, except that we won't have those like upper, under. So we will have goal 1, goal 2, goal 3. So we'll have like the goals here. Here we'll just have, we have 3 goals. Okay, so we'll just have the goals. Oh, actually, I should not have deleted those formulas. We should use them as the actual. Okay, so here I'll just say the actual value, and here these are the target value. I'll copy these back. And actually, we can just copy here. Sorry. we can just copy those again. Okay, and just unhighlight them. Those are the actual value. Yeah. Target value. And remember, what we want to calculate is the weighted percentage deviation. So the weighted percentage deviation is used to use the actual value, subtract the target value, divided by the target value. So here, I will just calculate after this. Will be percentage deviation. Okay, so the percentage deviation will equal to, okay, equal to this actual value subtract the target value divided by the target value. I need to enlarge this a little bit. Okay. Okay, so it's the actual divided, subtract the target divided by target. Then you can copy this down here. Okay, so that's a percentage deviation, then we will put weight. Assume 1 here. Okay, then here will be weighted percentage deviation. Okay, basically it will just be this times b equals to be this one times this one. Okay. So with this part, we have all the left-hand side calculated. Okay, and then for the Q is the objective function and also a decision variable. Okay, so we'll just set here. Okay, so that's the objective, which is the Q. We're going to highlight that in blue, representing that's our objective. And this is the first time that in the object function we don't have anything. It's not actually a function. It's just a variable there. Okay. Remember in all the previous problems we need to put, say, this equals to be a relationship, a combination of the decision variables, right? But here, this Q is both the decision variable and also the objective, and also the right-hand side of all your constraints. Okay, so we'll just highlight it and then we'll go to solver. So since this sheet is copied, so all the previous constraints are already set. Okay, and we need to change the objective. So change the objective to be this one. We want to minimize it. And make sure, okay, a lot of people make a mistake here. Make sure you add the Q to your decision variable part. Okay, so your decision variable will include those yellow shaded one and also the Q. And constraints. Add more. So weighted percentage deviation need to be less than or equal to this Q here.
Are we adding that on the previous constraint?
Add, yes, additional ones. because those ones are still, the previous ones still need to be met. Okay. Okay, find the solution. Click OK. Actually, I'm going to highlight these ones as.
The weighted deviation is greater than or less than?
Okay, so now if you look at I'll highlight these ones. If you look at your solution, the actual value of your total cost, total toxic water, and total accidents, they represent a good combination of the three objectives as compared to the target value here. So all of them exceed the target value to some degree, but this is a combination. It's not like if we solve the problem using the weighted percentage deviation, sum them together, minimize them, then we will get just one of those solutions with one of those objectives here. Okay, so with this, if you think, okay, for example, the percentage deviation, the toxic water achieved, this is really great, right? And the target part, so the cost part, say if you think, okay, cost is a little more important than me, change this to 2. Solve again. Okay. So the percentage deviation of the toxic water increased a little bit, but my cost deviation decreased to 4%. Accidents, I think it's similar from the previous ones. Okay, so this illustrates again. First, you find a combination for a solution that achieves the balance among all the three objectives. Okay, not just the one being achieved while the others not. And by changing the weight here, again, you can find a satisfying solution for yourself. Okay. Okay, so this is MOLP. And so we implemented this problem. And possible minimax solutions if we map them back. Okay, so when we change the problem to the minimax format, adding those constraints, the feasible region is changed. Okay, what I show here is only saying, okay, using the new solution and map them back to the original feasible region of that original model setup. And say when we have weight being 10, 1, 1, and that solution we get is somewhere here. Okay, and different weight will get solutions here. That's what we wanted to achieve earlier, because we don't want just those corner points represent extreme cases. We want some combinations. Okay, so some comments about MOLP. Solutions obtained using this minimax objective are Pareto optimal. That's what I talk about. So you can achieve balance. And you won't achieve one objective better without making another worse. Okay. And the deviational variables and the minimax objective are also useful in a variety of situations not involved in MOLP or GP. After you learn this, you can find creative ways to implement this minimax objective in other models, especially say like in a project. And for minimization objectives, the percentage deviation is the actual the actual value subtract the target value divided by target value, just like the one we just implemented, right? In the problem we just implemented, we have 3 objectives, all being minimization. That means like a better answer. So you won't be able to underachieve, because they are already the minimized value. So that's why we use the actual value to subtract this target value. Okay, because the actual value will for sure greater than or equal to the target value. Then for maximization objectives, say in some cases, in this case it's minimize cost. In some cases, one of the objective may be maximization, say to maximize the profit, at the same time minimize something. Okay, then for the percentage deviation for that one maximization objective, you need to use the target value subtract the actual value, divide by target value, because based on the same logic, right? If you find this target value by solving a maximization problem, then this target value you get is the maximum that you can get. And those target value will be less than or equal to those target value. Oh, sorry. Highlight the wrong place. Those actual value will be less than equal to the target value for sure. Okay, so we need to use the target value subtract the actual value so that we get a positive percentage deviation. Okay. If a target value is 0, which means you can put it as a denominator here, okay, then use the weighted deviation rather than the weighted percentage deviation. So you don't calculate the percentage. Okay, so this is some summary. So how to do the MOLP? We just went through one example. First, we identify the decision variables in the problem. What's the second step? Reflect what we just did.
We solve multiple objectives one at a time.
Okay, we solve multiple objectives one at a time. Okay, so you kind of like identify the objectives, right? Of course, to solve that, you first skip a few steps. So identify the objectives, identify the constraints. In order to solve them, you have to find the constraints, right? And then solve the problem once, okay, for each of the objective identified here. Okay, good. Then what happens next? Okay, set those optimal objective function value as the target value, okay? So that here as the goals, right? So you same as the target value, okay? Oh, I already gave this. Okay, what's the next step? We now know the target value.
Calculate the percentage deviation.
Okay, now we have the target value and we also have the formula that calculates the actual value. So we can calculate the percentage deviation now using the actual value and the target value. Okay. Okay, so create that deviational function. Okay. And what happens next?
New objective of Q.
Okay, so we introduced that Q, right? For each of those functions, yeah, we assign weight. So we have the weighted percentage deviation. And then we introduce this Q and make, what are the new constraints? What are the new constraints we added?
The weighted percentage.
Okay, the weighted percentage deviation all need to be less than equal to that Q. Okay, and why we call this minimax? We don't put the minimax as an objective function, right? Why we call this minimax? What do we put at the objective function? What's our objective function?
Variable Q.
Before that, what's that? We minimize or maximize? We minimize the Q, right? Okay, but why we call it a minimax?
That is the deviation. It shows the deviation.
Uh-huh.
And deviations are more than the target values.
Okay. We minimize the what?
Maximum of the deviation.
Okay, we minimize the maximum of the deviation. Because with all the constraint that the percentage deviation less than equal to the Q, we will find the maximum value of the deviation, right? Say like one of the constraint will be strictly equal constraint. And in that constraint, the right hand side would be the maximized So it will be the maximum value of the percentage deviation. Okay, and we minimize that. Okay, so we minimize maximum deviation, but in object function we only put the minimize the Q. Okay, solve the resulting problem with objective of minimizing the Q, and inspect the solution to the problem. Same, if the solution is unacceptable in cases where the weights are not given, then we adjust the weights, look at the solution, solve it, adjust the weights, solve the problem again, look at the solution, and if not satisfying, reassign some weights, resolve the problem. Okay, but if the weights are given, then you solve it, then you are done. For the homework problems in this chapter, the weights are all given. Okay, it's pretty easy to figure out. For example, kind of like goal 1 is 2 times important as goal 2, and goal 2 is 2 times important as goal 3. So what weights do you give?
2 and 4. 1, 2, 4.
4, 2, and 1, right? A is 2 times important as B, and B is 2 times important as C. So A get 4, B get 2, and C get 1. Okay. Okay, so that's the end of chapter 7.